Good morning, everyone. Welcome again, and thank you for joining this webinar on the life cycle assessment for bitumen, which will be organized in 3 sections. First, I will present the main assumptions and the main results related to this new study. Then we will look at the comparative analysis with the previous study and focusing on the global warming potential indicator. And finally, I will talk about the deliverables available for you and for everybody on the EuroBitume website. So let's start with the presentation of the LCA study. Well, we decided to start this new life cycle assessment study last year in 2024 for 2 main reasons. First, because we wanted to update the reference year of the data. As you probably know, the previous version, the version 3.0 was published in 2022 with an update in 2020 and an update in 2022. So 5 years after this publication and in line with common LCA practices, we thought it was a good timing to revise it, and you will see that it's more a revision than an update because significant changes in the assumptions and in the results appeared. I could add that the first life cycle inventory was published by EuroBitume in 1999. So as you can see, the environmental data for bitumen has been at the heart of EuroBitume's activities for a long time. The second reason is because in the critical review of the previous study, once again, the LCI 3.0, 2 main questions were pointed out. The first one related to the choice of a database for raw data, and so especially for the crude oil production. And the second was related to the lack of primary data used for the calculations. That's why we conducted this 4th life cycle assessment study. And it's a priority for EuroBitume to provide reliable environmental data for bitumen to stakeholders. And we do think that this kind of collective life cycle assessment is very important. And it can be considered as a reference and representative for environmental data. And for example, the previous version, the LCI 3.1 is cited in various documents and initiatives. For example, the product category rules for asphalt mixtures in Norway, as well as in Germany. At the European level, the European Asphalt Pavement Association refers to the EuroBitume value for its decarbonization roadmap. And the last example in France, SEV Eco Comparator software also refers to the EuroBitume value. So our ambition, is really to make the EuroBitume LCA a reference source in Europe. The study was conducted according to these different, following stages, I would say, in the conventional way. So first, data collection and data quality checks. I won't go into the detail, but we use this kind of iteration loop to make sure that the quality of the data was high. Then we had the calculation stage, the reports, the external review, and finally the publication of the results and of the final report. It's important to mention that we worked with the company Sphera, which is a company which has a good references in environmental impact assessment and has a tough experience in the energy sector. And I am pleased that we have a CIRA's representative with us today, Alexander Stoffringen, who will take part in the Q&A session after this presentation. And for the external review, we worked with the company Solinen, which has a great experience in critical review, and which is also, for example, involved in European standardization. We considered in the framework of this study 2 bitumen categories. First, an average bitumen, which is representative of straight run and air rectified bitumen, so covered by the European standard TN 12591, so mainly for road and paving applications. And the second bitumen category is the oxidized bitumen, rather for other industrial applications, including, for example, waterproofing or roofing. The study is representative of the bitumen production of Eurobitumen members in the EU and UK, so thanks to a data collection from 17 refineries in Europe, provided by 8 companies, and which represents about 75% of the bitumen production of Eurobitumen members. That's a good result, according to us, for a collective life cycle assessment. It's a very good representativeness. The scope of this study is, I would say, classical, the cradle to gate, which means that we included the crude oil production, the crude oil transport to the refinery, the various refining processes, and finally, the storage of bitumen at the refinery. So it's typically the same scope than in the previous life cycle inventory. The life cycle assessment study contains 2 results categories. First, what we call the life cycle inventory, LCI, which is a quantification of the different flows of resources and emissions associated with the bitumen production. And you can find in the full report the main flows of resources and emissions to air or to water, which is typically this table here. And for LCA practitioners who would like to access the complete data set, you can download on the Eurobitumen website through a request form this data set in the ILCD format for International Life Cycle Data System, which is neutral and interoperable, which means that it can be used in the different LCA software programs. In practice, it's not so easy because the ILCD format cannot be directly imported in all the LCA software programs, but we are working on this issue. Anyway, for the moment, you can download the ILCD format through a request form on the Eurobitumen website. The second result categories is the life cycle impact assessment, LCIA, which is the transformation of the different flows in terms of emission of our resources into impact categories. And we decided to deliver these impact categories in compliance with the standard EN 15804 plus A2, which specifies 38 indicators, including, for example, indicators related to the climate change. So, for example, the global warming potential indicator. But you can also find the other indicators like acidification, eutrophication, water use, waste, etc. All these 38 indicators are available in the full report. In the rest of my presentation, I will mainly focus on the global warming potential indicator because it's the most widely used indicator, I would say, in practice, and especially, for example, in public procurement or in contracts between stakeholders. So I will mainly present results on this indicator in the rest of my presentation. And this is the results of this global warming potential indicator for the two bitumen categories that I mentioned previously. So on the left part, you have the average bitumen. And the new reference number, as you can see, is 530 kilograms of CO2 equivalent per ton of bitumen. So it's basically the carbon footprint of the average bitumen. And as you can see, also the feedstock supply or the crude oil production represents the main part of this carbon footprint, around 70%. And the second most important stage in terms of carbon intensity is distillation processes, which represent about 14% of this carbon footprint. On the right-hand side, you have the results for the oxidized bitumen. So typically for this kind of bitumen, we have an additional oxidation process at the refinery, the oxidation process, which consumes energy and then has an impact on the carbon footprint. So typically this oxidation process represents around 14% of the carbon footprint of oxidized bitumen. And the total carbon footprint is 616 kilograms of CO2 equivalent per ton of bitumen. These numbers are significantly higher than figures available in the previous life cycle inventory, but I will come back later on this point to explain the differences. And if we zoom in on the carbon footprint of the reference average bitumen, you see again this new number, 530 kilograms of CO2 equivalent. And you have the distribution of this number according to the different production stages here and according to the different greenhouse gas here. So once again, the crude oil production represents the main part of this carbon footprint, around 70%. And then in order of the carbon footprint intensity, you have the distillation processes, the feedstock transport, and the bitumen storage. What is interesting on this chart is you can also see the effect of the different greenhouse gas. So in light blue, you have the CO2 emissions. In dark blue, you have the methane emissions, and you can see that the other greenhouse gas, including the nitrous oxide, are insignificant. So in the rest of my presentation, I will focus mainly on the methane emissions and the CO2 emissions. CO2 emissions represent just over half of the carbon footprint of bitumen, and methane emissions around 50%. What is interesting is at the crude oil production stage here, methane emissions represent the main part of this carbon footprint. So that's typically a new result compared with the previous study. And I will come back also later on this point. Just to finish about the results, you have here on this chart the result regarding the eutrophication indicator. The idea is not to comment this kind of results, but just to remind you that in the full report, you can access the 38 indicators and according to the different bitumen production stages. So typically this table that you cannot read on this slide, but which is available in the full report once again. So that's it for the first part of my presentation, and I propose now to move on to the next point, which is a comparative analysis with the previous study, and once again focusing on the global warming potential indicator. And on this chart, you see again the new numbers related to the new LCA study. So 530 kilograms for the bitumen and 16 for the oxidized bitumen. And on the left-hand side, you have the results regarding the carbon footprint taken from the previous study, the LCI 3.1. And in this LCI, we presented two types of results corresponding to with and without infrastructure. What we call infrastructure is the construction, the maintenance, and the operation of the infrastructures used for the bitumen production. So, for example, the refinery, the wells, the ships, or the pipelines, etc. And you can see that these infrastructures had a significant effect on the result. That was the observation taken from the previous study. In the new study, we decided to provide a single value for each bitumen category, one value for the average bitumen and one for the oxidized bitumen, because it was not so easy for the users, for the data users, I mean, to choose which of these value with or without infrastructure to use for their own calculation. So in the new study, we have a single value. However, we addressed this issue of the infrastructure effect in the framework of sensitivity analysis, which is available in the full report and in the result. What we observe, of course, on this chart is a very significant increase in the carbon footprint compared with the previous study, plus 145% increase if we consider the figure with infrastructure. So, of course, it is very important. And the idea of the next slides is to understand and to explain you why we observe such a difference. And it's very important to understand that the significant change in the results is due to significant changes in the LCA assumptions and the methodology. And that's why I present this table. On the on the left part, you have the main assumptions related to the previous study, the LCI 3.1, and on the right part, you have the main assumptions related to the new LCA study 4.0. And regarding the crude oil database, this is the main, probably the change that has the biggest impact on the result. In the previous study, we used the IOGP database, which is a database based on the geographical averaging by big regions, which I would say is not ideal because the variability of the carbon intensity of the crude oil within the same region can be very important. That's why we switched to another database in the new LCA. I can add that in the previous LCI, we used a 3-year averaging for the crude oil production, I mean from the year 2015 to 2019. So in the new LCA, we are now referring to the Spheras Managed LCA Content Database, which is based on an averaging by country of origin, which is considered as more accurate than in the IOGP database, which was, I remind you, at the scale of the region. And we are also more accurate in the way of modeling the methane emissions from venting, flaring, and fugitives. It's based in the Spheras database on the global methane tracker tool, which is published by the International Energy Agency, and which is based, for example, on the satellite measurements. So considered again as more accurate than what we used in the previous study. Regarding the crude oil basket in the LCI 3.1, we used an estimation by European members of the a crude oil mix with the reference year 2019. In the new study, we are now using primary data collected, as I mentioned previously, from 17 refineries in Europe. And for these 17 refineries, we collected crude supply data by country of origin. And then we weighted this data by the individual refinery bitumen production. And we also decided to use a 3-year averaging, meaning that we took into account the crude supply data by country of origin from 2021 to 2023. We also changed the allocation method at the refinery. In the previous study, we used the sensible heat method, which is a theoretical calculation of the energy required to heat the bitumen from the crude oil temperature to the bitumen temperature. So basically an increase of around 150 degrees. And also taking into account that there is no phase change. So using basically the heat capacity of the bitumen. So once again, it's a theoretical approach. In the new study, we are now using the allocation by energy. And thanks to data collected from, as I mentioned, 17 refineries. So we had this data for the 17 refineries, so we could use the allocation by energy. And for the bitumen storage, it's the same idea. I mean, we are now using primary data from this 17 refineries. And in the previous study, it was more based on the theoretical calculation using storage parameters and parameters taken from the literature. So if we come back to the impact of the crude oil database change, on this chart, you have the crude oil production stage in terms of carbon intensity of carbon footprint expressed once again in kilograms of CO2 equivalent per ton of bitumen. On the left part, you have the results taken from the LCA 3.1, so 153 kilograms. And on the right part, you have the new result. So as we already observed in the previous slides, we observed a significant increase. What is important to have in mind is the comparison is a little biased because in the new LCA, we use a different crude oil mix than in the previous LCI. But anyway, on this chart, we still can have this, I would say, two main observations. First, in terms of CO2 emissions, the results are very close for both studies. And the main change is due once again to the way of accounting for methane emissions. So typically, this significant change is due to the change in the crude oil database and including the change of taking into account the methane emissions. If we look at the effect of the crude oil basket, once again, we cannot compare directly the new result, I mean the new results taken from the study 4.0 with the previous study because the calculations were not carried out according to the same method and the same databases. That's why we propose to carry out a sensitivity analysis with 3 different scenarios. The first scenario on the left-hand side is the baseline scenario, which allows to obtain the new reference number 530 kilograms. and which is based on the 5-year averaging, so taking into account the evolution of the crude oil share over the past 3 years, I mean from 2021 to 2023. We considered another scenario taking into account the evolution of the crude oil mix over the 5 past years, so from 2019 to 2023. So you have this figure. It's presented according to, I would say, big regions. It's important to have in mind that we collected data at the scale of the crude oil by country of origin, but for, I would say, confidentiality reasons, it's presented only at the scale of big regions, but you have the evolution of the average crude oil mix over the past years. And for this scenario, we used 5 years, so 5-year averaging. And we also consider the last scenario, which is basically the year 2023, so only the last point on this figure. As you can see, the crude oil mix has a significant effect on the result of the carbon footprint. But we decided to choose this 3-year averaging because it is considered as a good balance with all the scenarios. You could mention that the scenario 2023 is more representative of the current situation, but we consider that we don't know how this crude oil mix will change in the future, in the coming years. So we propose to have a more, I would say, stable number based on the 5-year averaging. That's why we choose finally this scenario for the final, to obtain the baseline scenario and this new number, 530 kilograms. Oh, sorry, I had this animation. And finally, regarding the impact of the allocation method at the refinery, it's the same idea. I mean, we cannot compare directly the previous study with the new one because once again, they are not based on the same calculation and databases. So we, in the same way, decided to present a sensitivity analysis in the study and in the report. It's available in the report. So we have this baseline scenario based on the energy allocation, which allow to obtain this number 530 kilograms. And we made a calculation using the sensible heat method. So just to remind you that this method is a calculation based on the evaluation of the energy consumption to heat the bitumen from the crude oil temperature to the temperature at I would say to the storage temperature, and considering there is no phase change, so using only the heat capacity and the yield and the delta temperature between the output and the input. And so we obtain this table here in terms of energy consumption with the sensible heat method, and this table here with the allocation method by energy. So if you look at the total result of the global warming potential indicator, you find that the difference is quite low, between 2 and 3%, so has no significant effect on the result considering the total carbon footprint according to the different production stages. But if you look specifically at the distillation stage, you can see that the effect is significant. I would say around 40% between the allocation by energy and the sensible heat method. So, well, we are not questioning the sensible heat method, which is very helpful in many cases, but we preferred to use the allocation by energy for the baseline scenario because we typically have the primary data, and it was probably it was our choice to use this allocation method by energy because we had primary data available. And that's it for the explanation of the effect and the main differences between the previous study and the new one. And you have a synthesis on this chart, a kind of waterfall between once again the previous LCI in terms of carbon footprint. So on the left part, this bar on the left, 216 kilograms, and on the right hand side, you have the new number 530. And between both bars, you have the effect of the difference between both approaches according to the different production stages. So as you observe, I would say again, you see that the feedstock supply explain the major part of the difference between both results. And within this production stage, methane emissions, so the way to account for methane emissions, explain once again the major part of this specific stage. Then you have the distillation processes. So I mentioned just before, this is the effect of the change in the allocation method at the refinery. And here you have the effect also of the change in the method to modelize the bitumen storage stage. And you have, as I mentioned, the distribution according to the different greenhouse gas. So no comment about the other greenhouse gas because they have no significant effect, but you can see that methane emissions explain the major part of the difference between both studies. And just to summarize with words rather than with a chart, the three major factors influencing the global warming potential indicator increase are the change in crude oil database and crude oil basket, which explains around plus 100% of the crude of the carbon footprint. The modification at the allocation method at the refinery plus 24%, and the change in the bitumen storage model at the refinery plus 12%. So that's it for this comparative analysis, and I propose you now to move on to the next point, to the last point, which is the deliverables. So in terms of deliverables, you can access on the Eurobitume website the LCA reports, that we call the full report, which is the blue report here, which contains the life cycle inventory. I mean the main flows in resources and emissions, etc. You have the LCIA, so the transformation of these flows into impact categories, including, for example, the global warming potential, but not only. You can access 38 indicators according to the well, in line with the standard TN 15804, and you have also the critical review, which is of course a very important stage for the credibility of our study. You can also download the LCI dataset with a dedicated web page with a request form on the Ubiquitium website, which is a files package available in the ILCD format, so which can be imported directly in most cases in your LCA software. But we are also working on this. We are still working on this topic to make sure that our data will be could be imported in all the LCA software programs. You have this report in green, which is a summary and a comparative analysis with the previous study, focusing, as I mentioned, on the global warming potential indicator. So it's around 15 pages, I think, and this one around 80 pages. And finally, you have frequently asked questions available on the website. We have 8 questions at this stage, but it will be a living FAQ, depending on the feedback from this kind of event. I mean the webinars, but also discussion with stakeholders, and we will update it, improve it if necessary, to make available this kind of question and answers for you.